All right, folks, in this discussion on thermodynamics, what we want to do is we want to look at the zeroth through the third laws of thermodynamics. We want to end up looking at the entropy, the change in entropy of the universe, which means we're going to have to explore system and surroundings and universe. And then this is really just looking into the second law of thermodynamics. And then we're going to determine the spontaneity for a process. So let's go ahead and look at the laws of thermodynamics. So our laws of thermodynamics, the zeroth law says if A and B are in thermal equilibrium and B and C are in thermal equilibrium, well, let's look at this. If that's to say T1 is equal to T2 and T1 is also equal to T3, then by this logic we could say that T2 is equal to T3. And this is the zeroth law of thermodynamics, and we can use this quite a bit as we work along. The next law of thermodynamics is the first law of thermodynamics, and this is one of the laws that we've talked about this entire year. And this is looking at the conservation of energy. So whether it's a spontaneous or a non-spontaneous process, energy can be converted from one form to another, but it cannot be created or destroyed. Cannot be created or destroyed. So today what we want to do is we really want to start to focus on that second and third law of thermodynamics. So the second law states that for a spontaneous process, the total entropy of a system and its surroundings always increase. So what we could say is that the entropy of the universe, we'll say delta S of universe, increases for spontaneous process. Okay, and then if it's an equilibrium process, then delta S of the universe remains unchanged for an equilibrium process. And we'll look at this, we'll look at a specific example of the second law of thermodynamics. The third law states that the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. So if you think about this, if we are in a solid state, we have a lot of order, which means there's not a lot of disorder. But what happens as our temperature increases? Well, as our temperature is increasing, that freedom of our motion is increasing as well. Well, if our motion's increasing, that means the randomness is starting to increase, so our entropy is getting greater. So, but this is true for a perfectly ordered crystalline substance. Okay, well, what happens if it's not pure? So if you have a non-pure sample, maybe you don't have a perfect crystal. Maybe somehow it got cleaved in some way. So it's not, all the atoms aren't lined up in this nice crystal lattice. What we'll find out is, even if you're at 0 K, for a non-pure sample, the entropy is greater than 0. All right. So for the second law of thermodynamics, what we're saying, and we'll sometimes see this written as delta S total, or you'll see it as delta S of the universe. And delta S of the universe comes from the change in entropy of our system plus the change in entropy of our surroundings. So if delta S is greater than 0, that means delta S is increasing. So this would represent a spontaneous process. Whereas if delta S of the universe is less than 0, it means that our system is becoming, or it's becoming more ordered. So this would be a non-spontaneous process. And finally, if delta S is 0, this means you're at equilibrium. So let's go ahead and consider ice melting. So if we have an ice cube melting at room temperature, so what happens over time? So if we think about this, the ice starts out, okay, so maybe we have our glass here, we have water, and then we have some ice cubes floating in here. So as we look at this picture throughout time, eventually what's going to happen is now maybe our ice cubes are getting smaller. Maybe the glass shouldn't have gotten smaller, but I never claimed to be an artist. And then finally, at the final step in our time lapse, there's no ice left. So what's happened? Well, over time, what's happened is heat has been transferred from our water to the ice, and as that ice starts to absorb that heat, it melts, okay? So as it melts, what's happening is we're increasing the entropy, okay? Because the ice was very ordered, so those water molecules were in a crystal structure, and then as it melts, now it's starting to move around in that liquid form. So this is an example of the first two laws of thermodynamics. So the first law is saying that the heat absorbed by the ice is equal to the heat that's given off by the water. And overall, what we're going to see is, if we start to look at the entropy of this, is that the temperature of the beverage itself is actually lowered. So now let's look at a numeric example of this idea of, will ice spontaneously melt? So what we can say is that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And we can substitute in for delta S of the surroundings to put the heat of the surroundings over the temperature. So will ice spontaneously melt? Well, we know the entropy change for melting is 22.1 joules per Kelvin. So this is actually delta S of our system. It requires the surroundings transfer 6 kilojoules of heat to the system. So this is the process spontaneous at negative 20 degrees Celsius, at 20 degrees Celsius. Well, you should have an expectation of this. If it's negative 20 degrees Celsius, which we know is definitely below freezing, will ice spontaneously melt? Well, the answer is no. So let's go ahead and prove that. So let's look at negative 20 degrees Celsius. So at negative 20 degrees Celsius, we could write delta S of the universe is equal to delta S of the system, which is 22.1 joules per Kelvin, plus, now we're going to use the heat of the surroundings. So what we're actually going to put in is we're going to put in negative 6.00 times 10 to the third joules, because we need to get our units to match. We can't plug in kilojoules and add that to joules. We need to convert it to joules, divided by the temperature, which would be 253 Kelvin. So you have to make sure your temperature is in Kelvin. Then you need to watch your sign. This is negative because the surroundings providing heat. So from the perspective of the surroundings, it's losing that heat. So what will happen is we'll plug this in. Make sure you're following your order of operations. And we get delta S of the universe to be negative 1.62 joules per Kelvin. Okay, well, since delta S of the universe for this particular temperature is less than 0, what we can say is it's non-spontaneous. And that meets what our expectation was whenever we first started. So what happens if you have ice at 20 degrees Celsius? Well, if it's above freezing, will ice spontaneously melt? Well, we know that it will. So let's go ahead and plug in and show this in a quantitative way. So we have delta S of the universe, again, is equal to delta S of the system, which is 22.1 joules per Kelvin, plus negative 6,000 joules over our new temperature, which is now at 20 degrees Celsius, which is 293 Kelvin. And whenever we plug this in, we should end up getting 1.62 joules per Kelvin. So since delta S of our universe is greater than 0, that means this process is spontaneous. All right, so that concludes our lecture on the first 3 laws of thermodynamics and really exploring that second law of thermodynamics and calculating the change in entropy of the universe.